All right. So from the beginning, welcome everyone. Uh, this is Lambda One. This is Lambda One stream. Lambda One is a community where individuals really interested in mathematics and programming, mathematics applied to programming. We really like developing systems, very passionate about it, but that's not it. We're also very interested in sharing this knowledge and also applying all this knowledge into challenges that humanity is facing. So trying to solve these challenges because these are some of the most important and exciting at the same time. Probably our most important project that we have right now is Kratia, which is a model for collaborative decision making. You should check it out. It's in GitHub. But anyway, today we're gonna talk about domain-specific languages. Why are they important, and actually how they relate to mathematics through a concept called algebras. And we're of course gonna learn how to apply them into developing systems and programming. In this case, we're gonna use Scala, but I think these topics can widely be applied to any other programming language. So probably the one of the biggest challenges that we have as software engineers, and if you're a professional software engineer, probably this is one thing that eventually you've encountered in the past, is spaghetti code. It's when things get all messy, right? And I personally think that the main reason of spaghetti code is that we are not decoupling our code. So this means we are talking about many things in the same place. So in order to have non-spaghetti code, whatever code we're writing should only talk about one thing and one specific thing. And this is why we're gonna talk about domain-specific languages. So the first word is domain. This means it is a subset of the universe that we have, of all possibilities, right? If you're programming in Scala or in any programming language, you have all kind of things like strings, integers, and databases, and your business logic, right? Which is probably like users and endpoints and whatever, right? So when we say domain, we say we're gonna talk specifically about one thing. Maybe, for example, users, when we're in the business logic, users will be, and user management will be a specific domain. Trying to communicate with databases or through the internet with HTTP, then that's a domain by itself. And what we want to do is create languages that express things about these specific domains so that it becomes easier to develop around it. So when you're developing a DSL, the first thing that you need to identify are the subjects, or in this case, the objects. Let's not think about objects as in object-oriented programming. We're being very abstract. These are things, okay? And the other thing that we need to think about are verbs or operators. So if we were talking about, you know, a natural language like English, objects will be like the subjects, like things we talk about, and then operators will be like verbs. So what we can do with the things. So that's it. It's things and what we can do with things. right? So let's put a really simple example. Normally, when you're working or you're trying to develop your own thing, your own prototype on whatever you're doing, or you're professionally dealing with some customers, and you're talking about users and stuff, you will end up with some requirements that somehow they will come to you, and stuff like, for example, for this new MVP, we need these features. And for example, in this specific example, we're gonna create a registry, right? So it's a place where people can get their IDs, and they can use these IDs to authorize some actions, right? So you will get something like, okay, there must exist a concept of maybe a community or the registry. Sorry. So there must be, for example, a peer should be able to issue a new ID card, given that there is a requirement on the provided data. And maybe another requirement could be a peer should be able to change his nickname, right, or the name in his ID. Now, when we have requirements like this, we can easily already identify the things in our domain and what we should be able to do with those things. So, for example, we could start coding and say, okay, we know we have peers or users, so let's call them case class user. What else do we have? We have IDs, so ID card, right? And probably we have also something to save your a notion of a store, somewhere where we are going to store all the IDs and the users and the correlation between them. So let's call it members store. Okay. And now what we need to do is take these simple operations that are required for us to program and put them into code, right? So the first one is a peer should be able to issue a new ID. So then we write, for example, class, and then registry. So we're creating the registry, right? The population registry. So the first thing that we should be able to do is to register a new user, right? So in this case, it will be, we have a user and we return a new ID card. In this case, it is important that we're being pure functional. So this means no side effects, and we'll see why this is important. So one easy way to deal with state using pure functions is just to bring the state with you through the functions. So in this case, we can add a new argument, which is the store, members store. And this is already one of the operations we need to do, right? We somehow need to implement this function. So let's say somehow implement this function that basically given a user and a store, we give back a new ID card. So let's keep it like this by now. In here, what I can tell you is that we should see these three things as the objects, and register as one of the verbs or operators that we're gonna do around it. And as you might see, this is already a way to express programs around the registry. So we're gonna call the registry or DSL, and these ones we're gonna call them or objects. Now, we've been using domain-specific language by now, and probably you've heard this term everywhere, right? DSL, DSL, DSL. For example, SQL is a DSL. Why? Because it's a way to express things around the domain of data and retrieving data, right? Probably a big corporation will try to sell you a software saying, hey, this is our big DSL so that you can talk about business, right? But the interesting thing here is that DSL is really not the name that I would use, or the words that I would use, because DSLs are actually algebras. So we're all about combining mathematics with programming, and in this case, we're gonna stop using domain-specific language, and we're gonna start using algebra. Now, why is that? Well, before we see that, let me guys show you our GitHub. So this is our GitHub. You see it's Lambda One IO, and I'm creating here a new repository called Apprentice Resources, which will have several resources. For example, for this topic here, I'm gonna put some challenges that will help you learn some stuff, some curated lists from us of things that you can use in order to learn. And one of the things that I've already added is here, algebras. So let's see what is the definition of algebras. An algebra is a collection of objects. So we have a collection of objects and operators. And operators are functions that take one, two, or more of these objects and return another object within the same collection. So if we draw it a little bit more abstract, what we're saying is that there are operators, like, let's say, okay, yellow is probably not the best color. Let's see, blue. There are operators, let's say a star. This is a generic way of saying any operator. Let's make it binary in this case. Let's say this is an operator that takes two things and returns another thing of the same type. If you see there, they are all A's. We're being very abstract, but that is nice because then we are describing a lot of things. When someone says abstract, what we're really saying is we're describing a lot of things. We're being very generic, right? So in this case, normally when you're maybe hanging with some poshy functional programmers, and they're gonna start talking about operators, and a lot of them are binary in this form. But one way to view these things is actually view them just as functions. Like, for example, a star can be a function that takes 1A, comma, let's make this one X, and another A, and returns another A. And then, for example, in the specific case of the specific case of the DSL that we were creating, star is actually not star. Star is actually register. So register is actually one of our operators. In this case, it's binary, but it can be 1, 2, 3, or many arguments. And register, in this case, it is not our DSL, but it is our algebra. So then again, when there's people talking, hey, yeah, tactless final and the free monad, and we have algebras, right? What they really mean is that they created a DSL. They created a way to talk about a specific domain and a specific phenomenon. This is, let's say, this is our algebra, and let's say this is our operator, right? And then okay, and then let's see what else I have here about algebras. By the way, if you have any questions, just put it on the chat. You can put it on Discord. Please do join Discord, and I'm there 24/7. You can ask as many questions as you want. But yeah, so the second thing that we know about algebras is also that when defining algebras, one may find truths about these algebras and the relationships that the operators end up creating between the objects. So one way in which you can see functions is not just as a factory that transforms something, but you might see it as a relationship. So what relationship does user have with member store? Well, the relationship is that through register, you can get an ID card, right? So as you can see, we're being very expressive. And sometimes we find that these truths are always the case true, and we call them properties. We'll see some examples of properties in the near future. So, and also when we discover that these properties are absolutely necessary in order to define, for an algebra to be, then we call them laws. So let's say there are a minimum amount of things that everything must have in order to be, okay? So for example, in order to be a human, then we could maybe come to an agreement that the minimum amount of things that you need to have is a mind and certain minimum capacities of the mind. Let's say you also need a body, and then you can call it a human. But there are a minimum amount of things that once you discover them, then you say, this is a human, right? So this is very philosophical, but actually this is really, really, really good, because what I like to say is that us programmers are actually like philosophers. Well, why? Because we're actually applied mathematicians. Maybe you don't know, but there's a direct correlation between mathematics and programs. And each time you create a program, you're basically creating a proof. And mathematics is a great tool for us to actually understand a domain. And this is, and mathematics in the end is applied philosophy, right? Because it's actually both philosophy and mathematics, they wonder, what is nature? What are the things around it? I want to describe the phenomena around in nature. The only difference is that mathematicians, we have a formal method to prove that these are real things, right? There's a minimum amount of logical entailment, real truths, right? And this is important because what we want to do as programmers is to be sure that our programs are correct. And this is a very important assertion about our programs. We want to say that everything that we think about our programs, it is true. And when we reason with algebras, we actually can discover truths about our domain, about our DSL. But we'll see that in a moment. So, okay, there are the laws, and okay, both properties and laws are advantageous to understand the domain that the algebra is modeling, and as well to gain knowledge for free once we discover that a new domain fits an algebra. So we'll see what that means. Now, the next step is actually to implement this function here. Now, we could say, okay, a member store is maybe just a list of users which are we're member of. An ID card needs to have a unique identifier, right? Maybe a UUID. And let's say that the ID card has there's a nickname on it, right, or a name. And then the user, well, at least we should be able to uniquely identify it, right? And then here we could make a potential implementation, right? Like we could search in the store if it exists, right? So in the store dot store dot let's see, is there find, let's see, we could, okay, one possible implementation is to say, hey, let's filter to see if there's a user, and then maybe match over it, and if it's the empty list, then we add it. Oh, sorry, by the way, this register function, in order to keep the state of member store, then we will have to pass along the new state of member store, right? So case nil, and then case there's a head, right? So it exists. It's right there. Probably the member store is not only the user, but it's ID card, right? So in this case, we need to do compare against the first one and say, okay, if it exists, then okay, maybe we can only return the ID card that it's already in there, and we didn't change the state of the store, so we can return it. And then in case there is none, then we can return the new state of the store, so which is store. So the store needs the user and its new ID. So let's say new ID equals the ID card, right? With an UUID. We're doing a little bit of cheating because random UUID is actually a side effect, but handling side effects is not the main topic of this talk. And a nickname, right? So we said in the requirements, we say that register needs the operation register actually needs the provided data. So let's say that the provided data is the nickname, right? And then, so we add the nickname, and then we have the new ID, and this requires the user, right? User. This is a way of making tuples, but we can make it like this as well. So this is a new state of the store that will have the user, and we also need to return the new ID card, so that's new ID, right? All right. What is this? Store, and this needs to be members store. That's it. All right, this is a valid implementation of it, right? But what is the issue with this implementation? Well, the issue with this implementation is that we might want to actually access a database, not just use or notion of this store, right? What if say, okay, in memory store is no longer good, we actually need to access a database, right? So then we will need to add here, for example, the member store probably should have some kind of reference to the data store, and then we will start doing some SQL here. And what's happening? Well, our spaghetti code is starting to happen. That's the issue that we will have. We're then again starting to couple different domains into one algebra, which is not good. And then once again, what we want to do is to have complete independence of every level of the domains. So the first trick that I can give you is actually to separate your algebra from interpretation. The simplest way to do this is to use abstract types. So in this case, we make it a trait, and we make our operator abstract. Okay. And then what we do is that now, since this is an abstract type, we can provide several implementations of the same DSL. For example, now we have a registry in memory, which extends a normal registry. Blah, blah, blah. And then we implement this here. Bam. Registry. Okay, cool. So what we're doing here is separating the definition of our algebra, the objects and the operators, from the implementation. And then again, in the future, we're gonna build this into not just do this, but actually use type classes. And then the next level is to go to something like a tackless final. And probably if you're into this jargon and you're into the tackless final thing, etc., or even the free monad, you also hear people saying, hey, separation of interpretation, right? Free of interpretation. We have these algebras that are free from interpretation. And what do they really mean is this. is you have one place where you define your language. Then again, your language, which is things and verbs on top of those things, from what that language really means. Okay, this is one interpretation. So we'll call this this is our interpreter. Okay, and then we can use it in programs. For example, we can say now let's make a program object my rest of the server, let's say, and now I say, hey, let's say that this is the one which receives the HTTP request. What is a good example? So besides registering a user, maybe what you want to do is, okay, yeah. So post register, right? So this is gonna be our HTTP server. Now, post register, let's say it receives a request, right? So request. I'm just gonna use this type aliases, just not to use a full-fledged HTTP framework right now. So let's say is your request, and then you have something like decode register, which is something that probably receives your request and then returns the user, the string, and that's it, right? And then probably in the HTTP request you have a member store here. Store is of member store equals something. And then in post register we can do type response equals something, right? Oops. And this returns a response, and it's gonna be the user and the string from decoding the request, right? And then we'll probably have def encodes response, which is gonna be, it's gonna take the ID card and return a response. And then val ID card equals something, okay? And then val val response equals encode response of the ID card, and then return the response, right? So this is a very typical HTTP pattern. We receive a request, we decode it, then we use our program in order to do the operation, and then we respond, right? And then we need to create the ID card from somewhere, right? So we can say, okay, I'm gonna be able to respond to this request if you provide me a way to talk about registering a user, okay? And we have it here, right? It's a registry. So if you give me the registry, which is the way of talking about registering users, then I can say, okay, registry.register user string, and then, okay, and then probably here the store. And this is gonna work. And this is nice because now this is abstract. This is only the way, this is only the language. This is only things that we can do with our objects, with our operators. And then this is independent on how we're gonna do this. And actually we're doing this so that we can actually maybe remove this. Say, hey, I want to go back to my original design in where I didn't need to pass the state along, right? Maybe I want to do some side effects, I don't care. Maybe I do want to keep it purely, and we'll talk how we can keep things pure in the future. But the important thing is that this was the original plan, right? To have nickname and user be related through the register operator to return an ID card. Now, this register in memory, now it can receive the store as an argument. And let's say def side effect. For now, let's do it like this. Side effect store, right? And this is gonna take the ID card. Let's make this private. ID card, unit. This is a side effect, right? This is the signature of a side effect. And if by the way, okay, a quick preview on how to make it pure. Probably you're gonna use something like IO, but we'll see that later. So we have the new ID, and we return only the new ID, and probably here we execute the side effect of saving the ID card. Sorry, the new ID, right? And then in case it does, in case it does exist, then we can say exist.to and remove this one, and I think that's pretty much it. And now registry doesn't need the store, right? Now, what we have achieved here, it's really nice. We removed the necessity of applying a specific type of storing. We were using an in-memory list to store the registered users, and now it has completely been removed. It has been decoupled. Why? Because in our business logic, we're only talking about we're only talking within our language, which is this algebra here. And then what we do is that, let's say that let's make this another language. Say this requires a registry, and then maybe we can remove this one from here. We can remove this one from here. From here, and then we'll probably have something like the main function, where we initialize everything. So let's say, hey, my server. Well, first, the language that I'm gonna use, the registry that I'm gonna use, it's gonna be a new registry in memory, and the registry in memory, it's gonna require a member store. So registry store equals yeah, let's make it a member store, and then we create some. Actually, it's really easy. Member store nil, right? And then registry store, and then we can create a new HTTP server with the registry. And then let's say that, okay, we have a side effectsful function inside the server which actually launched the server, right? So say server.run. And voila. Now this is cool because now we actually can implement a different interpreter for our registry for something else, right? Actually, probably we want to use the registry in memory for tests, and now actually we should use one that will actually access a database to comply with our requirements, right? Registry SQL, let's say, and this requires an SQL database, case class database connection, and this extends our registry. And this requires us to actually implement the method, which is register and blah blah ID card. Here we go. And well, here we do something, right? Like accessing the database. Yeah. We do all the mumble jumble of SQL in order to actually do the process of registering a user and a nickname with a nickname, right? Now this is cool because now in our test, let's say object test, we have something very similar here, right? In which maybe we want to use a registry in memory, and then test the registry, right? Or actually not the registry, but maybe something that uses a registry. And in our main, what we want to do is actually test, change this from in memory to the SQL one, right? So in the main, we now initiate a new database connection, and instead of using a registry in memory, now we use registry SQL, which takes a connection to the database. Awesome. Now, what did we gain? We actually gained a lot because HTTP server did not change in any way. All of this code did not have to change in order for us to change the type of the registry. And this is exactly what we wanted. We wanted to decouple things, right? We wanted to say, okay, here we're only gonna make programs that talk about registering a user. I don't care about if it's in memory, if it's SQL, if it has or requires a new connection to anywhere. I don't care about it. I just want to create my program. And we did. That is very nice. So now what we can do is actually extend our algebra and say, hey, there are more things that we can do with this algebra, like for example, changing the name of a user, right? Change name of user with nickname string, and then probably I get a new ID card out of it. And then we will have to implement this new operator on every single interpreter that we have. And now we can use it to do more things with it, right? We can create new programs that are able to talk about registering a user. Now, algebras are actually not only useful for talking about business domain logic, they're good for talking about anything. So the thing that I really like about thinking about algebras is that you're delimiting yourself to try to discover the true nature behind phenomena. And this is very philosophical, and I find a lot of pleasure into doing this. But for example, let's say that registering a user could fail, right? It maybe, or changing the name could fail because there is no user which we can change his ID card nickname. So in Scala, what we will do is making it an option, right? Because otherwise, in traditional in traditional programming, what we will do is throw an exception, and this is horrible because there's nowhere in the type signature here or in the language that says, hey, this could fail. It's communicating nothing, and then it's really hard to track all of these exceptions that are appearing everywhere. And in this case, we're being very explicit, right? The types are talking to us. They're saying, hey, this might fail. As soon as you see this type signature, as soon as you see this language, then you already know, hey, okay, probably it's returning an ID card. Why would it probably return an ID card? Well, it's changing its name, so okay, maybe the reason is because not every single user will be in our registry, right? So option, what we need to realize is that option is actually its own algebra. Option is the type that is creating this small universe of things that might or might not be in there. Actually, if we jump to the definition, all these functions which are pure, we say this is the algebra of options, right? Options map is the operator on the algebra of options, and the objects in this algebra are the options and maybe functions, things that we can combine together. I think one of the most key words when we're talking about algebras is about combination. Every operator takes one or more things and then it combines them into something else. And in this case, option is great, right? Because now the programming language has provided us on a way of talking about optionality. What else? There are other more traditional algebras, like for example, you have integers, right? And we say, okay, let's create the integer algebra. So what do we do when we create an algebra? well, first we identify the objects that we're gonna use. So in this case class, this is something called a closed algebra. We'll see why, but are ints, right? And then, so first identify the objects of the algebra. And then second, we need to identify the operators. Trait int algebra. All right. And then what can we do with integers? Well, the most straightforward way of combining integers is to add them, right? So we say plus. Let's not make a symbol. Plus x and y get combined into another integer, right? The implementation is really simple. X plus x plus inner plus y dot inner. Right? And we say okay, let's call this okay. And then we say okay, we have our algebra of integers. Why? Because we have objects, integers, and ways of combining them, of doing things with them, verbs to apply to the objects, and then we can use them, right? We say let's create a function that given a list of ints, then we return just one by means of combination of plus, right? So this is very simple. So we fold left. So then, okay, we discovered that another magical thing about ints is that there is 1 0 element in the integers. Between all integers, there's a special integer that that if we apply this plus with any other, so if we apply plus some integer and 0, then we're just gonna get this one, right? And the other way around, if we get 0 plus something else, then we're gonna get that something else. We're gonna use it here in this program. So say, okay, I need my algebra of integers. So I need my ints algebra. So algebra dot 0, and then fold left takes first one of the members, then your accumulated one, so accumulated, and then what we do is we use our algebra dot plus to combine them, right? And this is a pretty nice implementation of it. And if you see, we're having a very similar pattern that we did when we were coding about our domain logic, right? We were I'm gonna comment this. So we had an algebra with some operators, that will do something with the objects, combine them into other things of within our logic. Then we had different implementations of the algebra, right? And we had a program that could use that algebra to do something else, and it was disregarding the implement or the real meaning behind the algebra. The only thing that he cared about is that he was able to talk about registering users. Now here it is actually very similar, right? We have objects, we have operators, and this is creating a language. We have a way of talking about integers, and we have a program that takes that algebra. It cares nothing about the implementation. The only thing that he likes is that it has a way to talk about integers in its advantage, right? In this case, reduce is able to do its magic. Now, one important thing, one powerful thing about algebras is that they can become generic, more general. Mathematicians have found that the typical algebras that we had before, like the typical traditional algebra, x plus 1 equals 3, what is the value of x? Well, you can use the equation in order to find the value of x. And then they said, these properties that we have found in our traditional algebra with integers or etc., we found them in other places. So we found that, for example, integers, they have properties, right? For example, they say, hey, this plus operator, it follows something. Well, it follows that it is the same. Let's create here. Okay, so it is true that if you have 3 integers, let's call it x, y, and z, it is true that if we first take our algebra, let's make this an object for now. In algebra, if we first add x to y, right? How this can be an object. Let's make this. Well, algebra in and then we say algebra. Okay, so if we first add x and y, and then the result we add it to z, it is equal than doing the same but in another order. So first first y and z, and then with x, right? So this is this. So this is just too many, and this is fine. Yeah. So probably you've seen this a lot, which means this A with some operator and then combined with the next one is the same than and this, right? And then this is a property, right? This is a truth that is always, it's always the case that for this algebra, this is always true. For every single element and for every, in any combination of this equation is always true. Now they found that there are other things that share the same property. For example, there is trait the strings algebra, and the string algebra, it's very similar. For example, we have a 0 element of strings, which is the empty string, and a string concatenation. Oops. And string concatenation, it's something very similar to plus. And what is amazing is that this assertion here, it's also true for the algebra of strings. So what happens is that we end up discovering something more general, something that applies to several things. And what mathematicians did is that they named it. They say, hey, these type of algebras, we're gonna call them a monoid. So instead of, in this case, in a Scala, instead of using or any type, we're gonna use these types, we're gonna make them a generic, polymorphic. We're gonna put it here. We're gonna make these operators, we're gonna make them abstract. And now we have an abstract algebra the same way in which we did for our registry. And the integer algebra and the string algebra, it's then again just interpreters of like we did with the registry in memory or the registry SQL. So or monoid is just a way of talking about combination of things. So monoid, then again, which is something that probably you have heard, seen in several places without exactly knowing what it is. Well, now you do. Monoid is just a DSL. It's just a way, a language to specifically talk about combination. And a specific type of combination, one in which there is a 0 element, which, so actually the 0 element property, we say, hey, the 0 element combined with anything else is just that other thing. Like the integers algebra. Let's make this an interpreter, right? So monoid is this is our algebra, and this is our interpreter, right? So the class, let's call it int monoid, extends monoid of integers. And let's make this no longer our funny types, but just int. Goes like this, right? And this is the interpreter, right? It now is doing real things with the types. And let's see if this property holds for the integers. Well, we check, okay, the zero element is 0, right? So instead of z, we're gonna put 0. Then the combination operator is plus, right? So we're gonna do plus, and then any other thing, right? Let's keep it a variable, a. Now this equals to 0 plus any other thing. But we know that 0 plus any other thing is just that other thing, right? It doesn't matter what a is, the result is gonna be that a. So 0 plus 1 is 1, 0 plus 10 is 10, right? So this equals just a, right? So this is true. We have proven that this is true. And actually the same thing happens with strings, right? So the string monoid extends monoid of a string, and actually our code it doesn't even change. And now when we do my program, instead of taking an algebra, you just say, hey, I will take a monoid. I will be able to do this for you for any single monoid. And actually the program, I don't even have to change the program. And the cool thing is that now it became polymorphic. When your code is polymorphic, it's really cool because now we can use reduce for anything that is a monoid. That we can use the monoid DSL to talk about it. And this is extremely powerful. In the same way reduce didn't have to change in order to apply it to different things. It's very equivalent to what we did with our HTTP server. HTTP server didn't have to change, right? It was using a registry, which is just the DSL or the algebra. The interpreters are the ones that will tell what register really means. So in this case, the in-memory registry is the one that does it in memory, and the SQL one in SQL. And then in here, then again, we have one program that is going to be using monoid as a way of talking about these A's. And it's providing operators, it's providing you with the ability to talk. And the string monoid and the int monoid are the ones that are going to actually say, okay, this is how it actually goes. This is the actual computation that is going to happen. Now, we were talking, so we said, okay, the zero element being something that does not affect when applying it to plus, and the fact that plus is associative, so that's how we're gonna call it. When it's the same to do x plus y and then plus z than doing y plus z and then plus x, then we say, hey, this is associative. Now it happens to be that those two properties are also the laws of the algebra. So why is that? These are the two things that are absolutely necessary for something to be a monoid algebra. And we'll use, and why, and then you will ask, like, why would we want to go so far and to something as complicated as trying to identify some laws that might or might not be applied to our thing, and why will we go through so much trouble? Well, the answer is because these are truths that we will keep and transfer to our code. For example, in this case, reduce was absolutely depending on the fact that a monoid is associative and that zero did not affect in any way in order to implement reduce. So for example, in this case, fold left is going to start with a zero element. What reduce does is combine all the elements in list. If the zero element in algebra does affect the plus operation, then reduce is bugged. Then we introduce a bug. If we create a monoid that which zero element is wrong, then automatically reduce is wrong. So for example, if we make a monoid which zero element is 1, then reduce is already it's gonna have a bug, because it's gonna be all the combined elements of list plus 1, and we don't want that. Now, as you can see, this is extremely powerful. This is really, really good, because through discovering the algebra, we were able to understand better these domains, the domain of strings and the domain of integers. And we found that actually they're very similar. And we're able to create programs that do not care about the implementation. They only care about the truths that are provided by the algebra. And we have polymorphic code, which means I create my code once and use it differently on different parts. Now, this is something that we could do also for our business logic. For example, say, hey, if we do register, for example, register should be idempotent, right? So idempotence is a really simple property. It's actually very, very, very simple. This property says apply F to A should be the same than applying F to A several times, right? So actually as many as infinite times. So what we are saying is, hey, this is specific operation, if you do it once, then you're good to go, right? You can apply it 1,000 more times, and it's always gonna give you the same. In this case, a register should be idempotent, because if the user is not in the registry, then we should register it and return an ID card. And otherwise, we should always return the same ID card, right? So we could apply register to the same user with the same nickname many times, and it's gonna give you the same ID card. Now, we just made we identify a property of register, and not just that, it's actually a law for registering. Why? Because the rest of the programs that will use registry, they will depend on the fact that registering a user is idempotent. It's within the documentation, right? It says everywhere, it is the law that registering a user should be idempotent. And what you can do is now do two implementations. One that is very simple, like the one that we did with a list, right? And you're like, okay, this is definitely true. I mean, I can test this implementation. Say, okay, register is idempotent. I've just proven that this is a lawful interpreter of our DSL. And it is easy to test, right? Because you just need to create an in-memory list and run it for several times and say, okay, is it idempotent? Now, if you have a more complicated and more hard thing to prove, for this thing to prove, to prove, like for example, you're doing the one with SQL, right? Let's say that is extremely hard. You don't have a database in that moment, right? Okay, sorry, I lost my train of thought. Well, the important thing is that if you prove that register is idempotent for both cases, right? Then these both are correct implementations of a registry. So I think that is the most important thing about laws, about identifying laws on your programs. That you have already the list of things that are absolutely necessary for something to be correct. And the cool thing about laws is that you actually can use mathematics and do actual formal proofs around it. But of course, that requires another set of skills that we all probably should get, and it is actually pretty cool. All right. So, on another note, what we did here, it's actually called a type class. When you use an abstract type with a type parameter on it, and then we use that type parameter on the abstract functions or members inside the trait, then we called this is a type class, right? We call it a type class. And let's say this is also a type class. And then we call this instance. This is also an instance of the type class. And then we call this the instance of the type class, right? So actually, every time someone gives you a type class, it's actually giving you an algebra. So this is very powerful. For example, there are a lot of type classes in the Scala library. There is ordering, for example. Actually, I can access it here. Ordering, right? And ordering, it is it has a type argument, right? And you can have different orderings of different types. You can have an ordering of integer or of string, and what ordering provides you, it's a way to talk about things that can be ordered, right? That is the DSL, that is the algebra, where T is something that has the phenomena of having an order. And these are the operators, right? Compare, less or equal than. Which begs for the question, okay, if ordering is a type class and therefore it's an algebra and the objects are the T's and the operators are these, then what are the properties? And actually orderings also have properties and also have laws, right? So for example, one of the basic laws behind ordering is that this assertion of ordering should be transitive, right? So if x is less than y and y is less than z, then x is less than z, right? The property transferred. And what happens in that moment when you realize, or someone tells you, hey, this is a property of this type class, or of this algebra, then you gain a lot of knowledge for free, right? Uh, for example, that transitivity is some type of associativity, right? Um, and actually, there's something similar to the something similar to the zero element, which is reflexivity, right? Everything is equal to itself, right? So then you can use this extra knowledge that you gain for free for your programs. So, and probably this is a part in which I tell you what is so powerful about using mathematics when programming. It's all the knowledge that you gain for free. I think this is extremely good, powerful, and important. We are engineers that are trying to fight every day against the complexity that that our systems are, right? Uber is huge. Whatever you're trying to do, I'm pretty sure is super, super, super complex. And when we have a way to talk about smaller domains, and then we have truths that we can prove about that domain, and not just that, but these are truths that are shared between more things, and then we are describing them through a more abstract layer. Then we gain the ability to share this knowledge really, really, really easily, because if you're peer programmer, if you're developing an API, and then you have other programmers that need to use your API, and you need to transfer this knowledge, right? Like, for example, if you're using Akka HTTP, right? That's an example. And they have their own DSLs or whatever. They have their own ways of talking about HTTP. And then they need to transfer this knowledge. Hey, these things behave in this way, and you should combine them in this way. But if these guys, they're giving you no properties, no ways to, in a more abstract way, describe these things and these operators and combinators, then you're left with starting from scratch. You need to understand everything that they're doing from zero. You need to go to documentation and understand it from zero. But for example, you have other libraries that prefer to take the extra step of actually finding the abstractions on top of what they're trying to do. Like, for example, HTTP4S. HTTP4S, what does it do? They say, hey, a service is just a Kleisli arrow, right? And then in that moment, it's actually, that moment is actually huge, because in that moment, whoever actually knows about Kleisli arrows, it gains all the knowledge of Kleisli arrows applied to the API that the library wants to expose. In this case, a Kleisli arrow is something very generic, and we know a lot of properties about it. We know it can be combined, that it can be chained, that there's an effect around it, and boom, from nowhere, you gain a huge amount of knowledge. And I think this is just amazing. This is really good. And this is something that we can do for our own programs and for our business logic, right? Let's go back a little bit. And I would say, like, this is the conclusion. This is the conclusion. And let's actually wrap it up. DSLs are actually just algebras. An algebra is just a collection of things and a collection of operators. Operators are relationships between these objects, or in other words, functions. And you can decouple your algebra from interpretation by making an abstract type or a type class. And you can have different instances of this type class or different instances of this abstract type that will add the meaning or the interpretation of the DSL. This allows us to do programs that are completely decoupled and that are extremely expressive because they will only be talking about the DSL and nothing else, and anything else that is not required, like if it's through HTTP or if it's SQL or if it's in memory, we don't care. So it's completely decoupled. And we can discover deep truths about our domain that will help us understand it and that will help us test it and assert it and actually find more complex truths. One of the most powerful things about mathematics is that showing things or proving things is constructive. It's composable, right? Like functions. That this means I can make a really simple proof about something, like, and then I find another proof about something else, and then I find a relationship between those through, for example, I find an implication, right? Given that this is true, and maybe this is true, then it implies a new truth. So we've created a new truth from other two smaller ones. In the same way in which we do functions, right? Functions, we can take a really simple function and then another really simple function and then combine them into a new function that is a little bit more complex. And we can go on and on and on until we basically created a huge complex system which is able to do a lot of things. In the same way with mathematics and logic, we can start with very simple truths and then go into very, very, very complex and deep truths. And this is why mathematics is so powerful and needs to be applied in science and everywhere. Because it's the only tool that we have in order to work our way into more and more complex truths until we discover something very deep about the DSL or about the algebra or about the domain that we're talking about, right? This domain might be physics, might be biology, might be the web service that we want to do, right? And as soon as we find that, for example, one of our members does fit certain properties, say, hey, I'm creating this new object, and I discovered that if I apply it with this function, then there is one zero element, and I can combine them two into one, and it is associative. Wow, this thing is actually a monoid, and now I can for free gain all that knowledge of monoid, and I can actually for free gain all the functions that actually use monoids. You gain the whole world just by doing these simple proofs. And that's just absolutely fantastic. And it makes the duty of a programmer to be less a code monkey and more a philosopher and a mathematician, which is more about thinking about the universe and what does it mean things, right? Well, I would say that is a conclusion. Please, now we have some time for questions. The viewers that we have right now, if there is any questions, it is a good moment to do so. Otherwise, we will otherwise we will wrap up soon. Well, meanwhile, thank you for watching. I'm gonna be doing this hopefully every Thursday. You'll find the recording on YouTube and please do follow and join our Discord. Okay, thanks, bye. That was lame. It was pretty lame. Hope to see more of this next time. Awesome. Thank you, Arcane Aronax. You know, I am new to this, and it is really weird to talk to the camera and then and to no one really. But I'm starting to enjoy it a lot. And